I'm start recorded as well. You see the lab manual that I was uploaded in the. So this is your practical file, which you need to do the power flow and overcurrent protection in DigSilent Factory tool. So there is about first 1 to 8 steps, and because of your better understanding, I try to provide and explain much details and providing a lot of screenshot in terms of the software, because this is the first time that you might using the DigSilent software. So many of you are the beginning user, new user, so I try to provide many screenshot so that I can able to explicitly explain the tools and the modeling parameters of the DigSilent software. So this manual, that is 25-page document, that is uploaded in the Blackboard for you, and the steps 1 to 8 will be discussed for the power flow. And also at the end of the power flow, we have to do the overcurrent protection, and I use SEL 751A feeder protection relay, which is also part of the DigSilent software. Already SEL have a collaboration with the DigSilent vendor, so they have the soft version of the relay models that is already available in the DigSilent library. So using that relay models, we should be able to do the at least a overcurrent protection that is part of the scope of this practical file. And of course, in section 6, if you look, when I done the load flow with the DigSilent, I will also able to compare the MATLAB simulation results and DigSilent simulation results, and come to a comparative analysis between these two platforms. What is the deviation in the load flow results? And then I should apply a three-phase fault at bus 2, which is a symmetrical fault. But as I mentioned earlier a long time, there is a separate chapter for symmetrical fault, but that is part of your chapter 8, and I already uploaded the notes for symmetrical fault for theoretical aspect. Hopefully next week I will done per unit system. If time permits, I will do symmetrical fault calculation as well next week. Otherwise, the symmetrical fault calculation will be teaching the following week. Okay, so let's go on to the next page of the document. So you can see from here explicitly there is a lot of figures that I provided, about up to 49 figures, because it gives more details about modeling aspect from the software, and for the new users it's a good source for you start. And this network that you know already, so this network is the same network that you modeled in the DigSilent, and chapter 5 when we discuss the same thing. So I'm not going to go through this network. Your bus 1 is a slack bus 2 is a load bus, and bus 3 is a PV bus and generator bus, and the data is given in table 1. And again, some of the calculations that we discussed in the last chapter also, the same thing is coming up here. Example, if you have a base base impedance and converting the line impedances into per unit to actual values, the calculation step that we discussed already in chapter 5 is the same calculation is sitting here. So I'm not going to repeat. I hope you understood, unless if you have any questions to me. And the other thing is, the only thing that I want to speak about the transmission line current. In DigSilent software, when you use the transmission lines, you have to include your line current. And in order to find out the line current, so the line current is not part of the data that is given, but actually we should be able to calculate the line current based on the calculation steps that is given in this manual. For example, the real power P is equal to 3 phase power root 3 VI cos phi. So in this case, we need to find out the line current, that is a load current IL, that is equal to P divided by VI cos phi. So I think the root 3 is missing here again. Please take note, the root 3 is missing here, but in the steps is here. So somehow when I doing it's a typographic error, the root 3 is missing here. So we substitute, because our load is 400 megawatt and 250 megawatt. So the load current is 400 into 10 power 6, and the bus voltages, all the three buses are acting at 25 kV. And the power factor, we are assuming the power factor is 0.9 in this case. If it is a 0.9, we calculating the load current of 10.2 to 10.264 kiloamps. So this is step one, option one, to calculate the load current. In option two, so it means option one, we calculating about 10.26 kiloamps, and option two, we use a different formula, which is apparent power equal to VI. And in our case, our apparent power we assumed as 100 MVA, and then the voltage is 25. So you divide this thing and we getting 4 amps. It means 4 kiloamps. So option one, we have 10.26 kiloamps, the load current. In option two, using this formula, we getting a load current of 400 amps. Let me proceed that. So you can see the option 2 with 4 kiloamps is less than the line current, which exceeds 100% line rating and is the line. Therefore, the bus 3 bus network load flow simulated in the line. So it means I use 4 kiloamps, and for 4 kiloamps the line loading was excessive. So we assume the second option is not a good option. The first option, which is having 10.29 kiloamps, is a good option for the modeling of the network here. um, but these things I can take you directly from here to the DigSilent environment, but quickly scan through the document before we go into the DigSilent software. So this is a network that is modeled in the DigSilent network. You can see the 3 bus network and conducted the load flow as well. And the next picture is showing about the data of the bus. I think from here I can quickly take it to the DigSilent software. We can model the network from the scratch, and then we can come and verify this document. That will be the best idea to go around. Okay, let me stop it here. Okay, do you have any questions at this stage on the manual when you went through it? I just want to put my software in place before I scan again. Now I'm going to share the whole screen so that you can able to see if I go anyway. Can you able to see my software? DigSilent? Student? Can you
Yes,
confirm anyone? All right. So when you open the DigSilent software, so the first open page looks like this. But unfortunately, the software is installed in the lab. So this recording will be made. This section is recording already. So today you just observe, but next week, God willing, if you manage to access to the campus, you will practice yourself. Alternatively, we can also able to provide the lab during the week other than Monday as well. But you need to inform me when you want access to the lab so that I can put you through the technical team to find out when the lab is be available for you. But maybe I should leave this option to class rep. Yesterday, even one of your classmates asked me if the lab is possible to open on Saturday as well. So she did wrote the email. I still need to contact the technical team to find out the availability. But in that case, I will tell the class rep to leave this option. If you want to use the lab other than your scheduled slot on Monday afternoon, please write me an email so that I can forward the email to the technical team and copy you as a class rep, and then you can directly engage with the technical staff to find out when the lab will be available for you other than the Monday slot. When you go to the new project, so file is a new project for you, and then I can say 3-bus system. So for you is a 3-bus system example. The grid of the 3-bit system is 58. Owner name, you can use your names. All right. And then we open up the network. Here you can see on the left side there is a drawing tools. So we can able to see all the power system components from the drawing tools. You have a bus bars and you have switches, lines, transformers, generator loads, sources, and etc. etc. But this is the first exercise for you. Could be a little bit familiarizing yourself. Then it will be used for you the tools. I'm using this DigSilent software more than, I'm not sure how many years, 15 years or 20 years. So it will I might be familiar, but again the practice makes you perfect. So let me put the network like as it is in the SLD diagram. We have bus 1, so I put bus 1 here, and we have bus 2. There is a bus 2, and then there is a down as a bus 3. So I just left click once and bring bus 1, bus 2, bus 3, and once it's done I just need to escape to stop. Let me do it like this. This video is recording. Let's stop and record from the scratch again. Is fine. Yeah, we can continue. So then this must be oriented. So I can right click and rotate. Okay. So this is my bus 1, bus 2. Can zoom it as well. Can able to see it. Bus 1, bus 2, bus 3 clear. Now in DigSilent you just put the buses as per the location in the SLD, because you remember the SLD is here. I just need to open parallel to you. Can you see the bus 1, bus 2, bus 3? This SLD as it is. I have modeled in the DigSilent here. Okay. Now we need to define the bus voltage before you do anything else. So here this is bus 1 and the voltage is 25 kV. And as per the data for all the buses as is supposed to be, this is bus 2, 25 kV. The rest of the data, A-phase and 3-phase technology, we leave it as it is. And the internal cubicles is also changing. That's fine. Okay, I think you can leave it like that. Bus 1, bus 2, bus 3. And the next step is we have to connect the generator 1 on bus 1 and generator 2 on bus 3, and then the load on bus 3. So let's do that. Or otherwise I can connect the lines if we go on. So this is a line. So this is bus 1, 2. When I click this bus 1, you can see here this is called as a cubicles. So the bus 1 which have cubicle 1 to 4. So I have to select which cubicle I'm connecting bus 1. So it means this is the internal of the bus itself. In your presentation of the notes itself, I did explain the bus cubicles, which I quickly take you there. There is a slide picture number 29, figure number 29 is a bus cubicle. So this is a bus, and bus 1 having 1, 2, 3 cubicles. So cubicle 1 is connected generator, and cubicle 2 is connected with line 1, 2, and cubicle 3 is connected with line 1, 3. If I take your SLD diagram here, If you take a SLD diagram here, if you see this SLD diagram and this cubicle diagram, because this is bus 1. In bus 1, how many components are connected? Generator 1 is connected, line 1, 2 is connected, line 1, 3 is connected. So that's what, if you're looking at this cubicle, this is bus 1 and all these 3 components are connected to each cubicles. Are you with me? So now if I want to connect line 1, so the bus 1 having 4 cubicles is asking me which cubicle I need to connect my line 1. So let me escape this thing. So rather I should put first generator and then the line coming up. So it means the generator here coming back here as per the diagram we given here. So you see this a synchronous machine is a generator, it's representing on the network. So we're going to use a synchronous machine. This is your synchronous machine. So we're connecting on bus 1, cubicle 1. Can you see that the machine 1 is connected in bus 1? And then this another machine is connected in bus 3 and is going to internal cubicles. I select cubicle 1 of bus 3 is connected. So there's only 2 machines. And then there's the load is connected in bus 2. So where is the load? Yeah, there is a load, general load. So this general load is connected in bus 3. Sorry, in bus 2 in cubicle 1. Right. But this must be connected on the other side. So I can rotate it, flip-flop the node. So I flip-flop the node, so it means it connected on the other side. Right. Now we have to connect the transmission line. So transmission line is here, connecting bus 1. So you can see when you come to bus 1, already your generator 1 is connected on cubicle 1, so is not available. So the rest of the cubicle is available. So I can select the second cubicle and then that's the sending end. I want to see where is the receiving end is. This side, then in the receiving end, already load 1 is connected in bus 2 in cubicle 1, but cubicle 2 is available. I click that one. And then we have to connect between bus 1, 1 and 2 is connected. Now 1 and 3. So 1 and 3, because bus 1 is already have internal cubicles of synchronous and line 1, and now I need to connect my line 2, which is line 1 3. And then here I must connect. Okay, I'm done all those connections here. Okay, now we need to go and edit the parameters of all the devices. For example, your generator 1. So if you look at your generator data here is given. So the bus data we already did these things. Your bus 1 is 25 kV, bus 2, bus 3 is 25 kV, done that one. Now we're going for a generator data. Generator data, if you look at here, is synchronous machine G1 and apparent power 100 MVA, rated voltage 25, power factor is 0.95. And then we must also mention this machine as a reference machine. It means it's a slack bus, and the slack bus means we need to produce a voltage as constant. And what is a constant voltage? It must be 1.05 and angle of 0 degree. So these are the two parameters that need to be done for machine 1. And here the name we can put D1, and then this is the reference bus, and here you change the voltage, and here the voltage is 1.05. Then you go to the basic data, and here you can select new project, and then synchronous machine type G1 is supposed to be 100 MVA, 25 kV, 0.95 or 9. Let me check. 95. 95 kV, and the three-phase star rated. So all the parameters, repeat it. And then the machine 2, the generator 2, if you look at here, it's a 200 megawatt, 200 megawatt MVA and 25 kV and 0.9. Perfect. And then the other data, this machine is also constant V, but we're not specifying as a reference, but we need to specify your V and the power. So let's see here. Is it 1.05, 1.04? 1.04, and the react power is 200. Basic data, new project, 100 MVA, 25 kV, 0.98. Yeah. It's not necessary options, but let me check here what I did. Okay. So the generator data is done. Now we can go for the load data, which is industrial load, commercial load. You can specify, you need to select a new project. I think it's 200 watt and 250 megawatt. All others are constant maintained. And then the line 1, 2, 1, 3, and 1, 4. Okay. This is line 1, 2, and then you can select the line type. Okay, we need to select a new project for the line type. Basic data is the line 1, 2, 25 kV, and here the rated current. Remember, we calculated 10.29 kiloamps. This is what I spoke to you on the notes. Let me take you there. Remember here, we calculated 10.26 kiloamps. And then what is the resistance and reactance in ohm? Resistance and reactance in ohm in the first one, we should have 0.125. And then the reactance, what is the reactant? XL equal to 2 pi FL. So L is there, and you need to multiply this one with respect to 2 pi F. So what is that one? Can you able to calculate 2 pi times of 50 into 0.08? What is it? Anybody? Which is this value? I'm getting it, but just need to confirm. 25132. Is that right? This is, that means is a 2 pi f, 2 pi times of 50 into this value 0.0080, so which giving you 0.2125132. This is line 1 2, and then line 1 3, 10.26, and overhead line 913 0.06125. Then the reactance, we multiply this value with respect to 0.15, and then line 2 3. 2 3, this one 0.07. 0.00323. It means 0.15, 1570. Okay, and this one I need to check here. 13, 13 is this one. It means 8884. Okay, I'm basically done the load modeling of the network, and I should be able to conduct the load flow. Can you able to see still the screen? Let me do the load flow. So I can able to conduct the load flow, and for animation layers, I can able to click my power flow. So animation, so I can see the power flow as well, and I can able to see the load flow results. To compute the results, I can go here, put the complete system report, and all of them execute, and the report is generated. Let me look at the report. So the load flow is computed in 3 iterations, and then I can see from here the load is 200 megawatt real power and real power of 250 megawatt, but the load current is getting 7.48, and the line 1 2 is 3.13, and then the line 2 3 is 4.48 amps. Is this currents make sense? Bus 2, bus 2, 30% loading. Okay, let me check our results. It's what I did. Voltage profile. Okay. Bus 2, line 1 2. Line 1 2. Let me maximize here. So 5.71, but bus 2 is 11.3, 4.7, and 6.48. What is our results here? Little bit deviation. Let me check the parameters. Do you have any comments for me? No. Not saying anything. Let me check the parameters quickly if I'm right everything. So the load flow default 1.05, that's right, reserve machine. And then this one is 200 megawatt and 1.04. And then the load supposed to be basic data 200 and 250 megawatt. And the voltage is 1.8, it is assumed. Then the line 1 2. Line 1 2. If we are looking at my basic data, 10.246 kiloamps. Mhm. 10.2640. The resistance for line 1 is 0.008. Oh, I see the resistance value is 0.125. That's fine. And then the reactance is 0.2153, which is, if I take this value, 2.5 times of, yeah, which is 0.215132. That's right. And then line 2, line 1, 2, that is line 1, 3. Line 1, 3, 0.0625. One three 0.06 and the end 0.0260. And 2 3 because this is 36 percentage, this line is loading 46 percentage, but here I see is 30 percentage. Unless if I change this current to 4 clamps, okay. I think we can take a break here. This 12:20 past 12. I don't know, maybe we should take 40 minutes break and we can do by 1 o'clock. And then I will try to fix this load flow and we can do the protection on this network and conclude this practical. Is it fine with you? Hello, students? So can we meet 1 o'clock? Maybe if we meet 1 o'clock, hopefully by maybe I need another hour. So probably most probably by 2 or past 2 will be done. Okay, I'll stop recording here.